right, testing. Hey, good morning. Oh, wait. Do I need to? Whoa, I really went to town with my haircut this time, right? I look super slick. I have so much white hair. Look at this, all this grays. You know, this used to be black hair not so long ago. Oh boy. Anyway, good morning. How is everyone doing? Good afternoon, good evening, whatever this might find you. Hi, Karthik. How are you doing? Good to see you. All right. Welcome again to another live stream on Parametric Camp. If you're new to this channel, if you're new to what we do here, my name is Jose Luis, and I run this thing called Parametric Camp. We do live streams roughly every week. We've been doing pretty well lately, and we record tutorials on general topics of computational design. If you want to learn more about what we do, maybe follow us on social media, and then you can also get to know when we go live. Otherwise, there's a Google Calendar in the description of this video that you can subscribe to learn when we go live. And also we have a Discord server that we use to keep conversations throughout the week and ask questions and all that social stuff, remote stuff that we do these days. Which is actually has been pretty active lately, by the way. So what are we doing today? If you follow the channel, you probably know that we are in the middle or like trying to wrap up this playlist, this course, this seminar, or however you want to call it, called Advanced Development in Grasshopper. And we finished a big chunk, which was C# scripting in Grasshopper, and we're transitioning now to pure development, to native development of plugins in Grasshopper. Last week, I was wrapping up an exercise about custom previews in Grasshopper components. I needed to try a few things out, so we were prototyping throughout the live stream last week, and then it took so long to prototype that we didn't actually get to doing anything or to actually recording the video. So what we're going to do today is we're actually going to record the video based on the prototypes that we did last week, and hopefully, if we have time left, we're going to continue recording new videos on native plugin development in Grasshopper. And Victor is bringing up a very good question. Victor, we didn't have time last week to actually record the video because prototyping the exercises took us so long that we didn't actually record the video. So from last week, there's no video to edit and to publish. Hopefully, we will do that this week. So I'm going to record an actual video that we will edit and we will publish. Merhef Lotfi. No, Lotfi. I'm not sure if we've met before, but welcome to the channel. And Timothy, good to see you too. Kiburin, I also don't know if we've met before, but you're also welcome to the channel. And Victor, yes, you've been missing 2 weeks. It's absolutely okay. We all have lives, we all have stuff to do. I hope you're actually very busy and doing a lot of really cool things. Anyway, so we're going to start. Let me set up a few things here. So I'm going to open some Rhino, as you probably can imagine. So we're going to do some Rhino today. We're going to do some Grasshopper. What else are we doing? We're going to do some Grasshopper. And I always have this question, should I be on the left or on the right-hand side? So what did we do for the previous videos? Look, we're live. Ha ha ha. So this video is going to go here into the advanced development in Grasshopper. So it's going to go here, and I was on the left-hand side. So for this video, I'm going to stay on the left, but I think for the next section, I'm going to move to the right-hand side. So I'm going to stay here for the time being. Beautiful. I also want to take a look at the Grasshopper player, but I think that's a topic that I have somewhere. It's probably not going to make it to the advanced development list. And So, and then in pcamp files, I'm going to throw here the preview components that we were working on last time. And wow, it's taking a lot to load. And I'm going to drop this in here. Ooh, and my coffee is brewing. I'll be right back. Give me 1 second. All right. Okay. Have I shown you my Parametric Camp mug? Parametric Camp. A friend of mine made this and gave it to me. My friend Juan Adolfo, if you're watching this is back from the times when Parametric Camp was actually a workshop that happened in person. That was like 10 years ago, at least. Very nice. Okay, so where were we? Maybe I should make some Parametric Camp swag so that people can just go and get Parametric Camp mugs or something like that. I don't know. That would be cool. And t-shirts and stickers. We need stickers, laptop stickers, right? Yeah. Okay. So we were doing, this is what we did last week. Yes, this is what we did last week, which was, what was it? It was vector displays. It was a vector display and it was vector display. All right, this one here, okay. Excuse me. And where's it's an internalized point? Oh, I see. Okay. So, wow, what's going on with me today? ICB Phoebus, how you doing? Good to see you. I saw you yesterday on Nono's chat, right? Hey, Nicholas. All right. Give me 1 minute to think through what I want to do. Back to display limitation. Okay, so I'm going to copy some of this all the way here in my side screen so that I have like a cheat sheet of what I want to do. Okay. Is this what I want to do, a cheat sheet? And this is not what I want to do. I can just keep it here, right? I guess. Yes. I can probably just keep it here. All right. I'm going to hide all of this. I'm going to hide 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 this. Okay. No, not hide. Not. Just want to hide it. And then preview components. And it's going to be prototype. And what I want to do is I want to actually start a real thing with the files, starting from the file from the previous one, which is going to be this one here, review components. Okay, yes, all right, and then we're gonna start from here. Document components, and then I'm going to start from here. preview components. Yes, exactly, Nicholas. Yeah. Okay, and then we were going to do that. We had this. We had uh, okay, and then I want to I don't know what I'm doing here really. Okay. Let me just, my OCD is killing me right now. So, and then I have all this like hidden geometry, which is not useful. Can I start a different file? Let me just, sorry, my OCD is killing me right now. I can't work like this. Prototype. And then I'm just going to open another file, which is going to be this one. It's going to open this. Okay, and then I'm just going to show all. All right. So that's fine. And this is all. Why is this? Why is it doing zoom extent so big? I don't know. I don't know. Anyway, I'm going to hide this fault here. And for preview components, we are going to do custom rendering. I'm going to place this here. I'm going to start with a point that is going to be somewhere here. Okay, like a point somewhere here. And then yeah, this is, I'm a little fussy today. I don't know why. I'm all over the place. Maybe because I didn't have my coffee yet, but yeah. Color, display length, and scale. Okay, and I'm just going to remove everything here. And I'm going to remove all of this here as well. Yeah, we're going to start from scratch. All right, let's start from scratch because otherwise I'm going to be making a mess and none of us want that. Let's start from the beginning. The beginning is already typically a very good place to start. So the video we're recording is an exercise where we're going to be doing preview components that preview and have custom rendering of multiple things. The video will start eventually with me showing the thing working completely. But since we don't have that yet, what I'm going to do is I'm going to start with the first component. I'm going to record everything and then we will record the introduction. Okay? As we typically do. All right, so let's get started. Whoa, it's been a while. Are we ready for this? Okie dokie. Let's get started. The first component that we're going to do is going to be an extension of the component that we did in a previous video, which is going to be a custom rendering for a particular vector. And in order to do that, I've already pre-added some code here. I've created a point in Grasshopper that I have internalized, and then I can move it here in the Rhino viewport, and then I have created a vector from custom components. We can't really see it yet. That's what we're going to be doing in this exercise. And then I created a simple C# script component that takes an anchor point and takes a vector and will hopefully render that vector in three-dimensional space with a custom preview. So as we're going to follow a very similar structure to what we did in the previous video, I'm going to add all the overrides that define custom preview parameters, okay? And then what I'm going to do is that I'm going to create two global variables in the C# script component that are going to keep the values of the point and the vector. And I'm going to then use those global variables to read and to generate the custom viewports, the custom viewport wires. All right. So I'm going to create a point. I'm going to create a point 3D object P, and that's going to that's going to be the anchor. All right. And then I'm going to create a vector 3D object, which is going to be the vector. And then every time the component executes, what I want to do is I want to assign to that global variable, I want to assign the value that is coming in, and to the other vector global variable, I want to also assign the value that is coming into the component. I need to do this because, again, these two components, these functions, the functions that do custom preview, are outside of the run script method, and therefore these functions do not have access, are not in the same scope as the arguments, the inputs that come to the component. That's why I need to do this process of taking the information that is coming into the component and making it globally accessible by copying or by transferring it to a variable that is in the global scope. All right, we saw that in the previous video. And then in order to draw the arrow, it's going to be just as simple as saying, well, let me arguments display, and then draw an arrow, and then the arrow takes a line as an input. All right. So right now we don't have a line. So something that we can do is we can say, well, maybe what I can do is I can create a line object that I'm going to call an arrow. That's going to be global. And then what I can do is also during the execution of the component, I can say the arrow is going to be a new line that goes from anchor to, and uses the vector as the direction. Okay. And then I can use that arrow object. And then for the time being, I'm just going to be using system drawing color and, for example, coral. All right. I'm going to execute this, and if I turn the pre-visualization on, you can see that I can see my arrow. All right, that's good. Now I'm going to also, if you remember in the previous video, we said that it's important that we set the clipping box, because if I make this arrow too big, the viewport may not be rendering the whole area, the whole volume of the arrow, and then the arrow might be missing the actual arrow or some part of it. So it's important in the clipping box method to make sure that we calculate a bounding box that contains all the geometry that we want to render with this preview. The way we can do that is we can say, well, whenever you calculate a bounding box, I want you to calculate the bounding box of the line object so that the whole line is inside of the visible bounding box of this preview. So what I can do is I can say, can you give me the bounding box of the arrow? And this is going to have no visual effect here because we already were seeing the whole arrow, but it's going to make the whole process more resilient. All right. Now, this is what we did previously. And in the previous example, we also added the length here in the tiny corner, here. But what I want to do is I want to expand this exercise and add perhaps a few more inputs. So for example, I would like to control the color of the arrow. So I would not like this color to be hard-coded. I would like the user to be able to control that color. I would also imagine we have a lot of arrows and we're previewing all of them. If we have the text here, all the text would be drawing on top of each other, and it will get very messy, will be really unreadable. So something that I also want to do is I want to display the text kind of at the tip of the arrow, so that we can see which text, which length belongs to each arrow, and whether if we want to display that or not. So let me set up a few things here, and then we can continue the exercise. Okay, so we're going to copy this. I'm going to paste it here, and I'm going to paste it here, and then I'm going to say what this is going to be. It's going to be C. This is going to be color. This is going to be a boolean. Sorry, this is going to be length, and then this is going to be the size of the length, and the size of the length is going to be also some kind of slider, I guess, right? It's going to be a slider, these two. And it's going to be true, and it's going to be here, yes. Oh, I'm excited about this exercise, actually. I think it's going to be quite very cool. Parametric Camp. Where are you, Juan Adolfo? I miss you, man. Okay, so what else now? So we're continuing the video. As you can see, I have taken the time to add a few input parameters. So that's one of them is going to be a color that I'm creating with the Grasshopper component, color RGB, which outputs basically three numbers that go from 0 to 255, representing a color in the RGB space. In the C# script component, I have added three inputs. One is going to be C, so that's going to be the color that we want to color the arrow with. L is going to be whether if we want to display the length of the vector or not, so that's going to be a boolean, and I got it here. And size is going to be the size. This is going to be the size of the text for the length of the arrow. Okay, I have done it CLS, and I need to make sure to remember to type these inputs. So here it's going to be item, and then the type is going to be, you're not seeing it, it's showing up on my other screen. The type is going to be, for this one, is going to be of the type color from the system. L is going to be a boolean, and S is just going to be a double. All right, beautiful. So because all of this, the color, the boolean, the size, all of this is information that is going to be needed in these global methods. I'm going to do the same technique. I'm going to create variables in the global scope to handle them, to store them, and then I'm going to pass that information to the global variables. So I'm going to say, for example, I want to create a variable of the type, and if you don't want to be typing system drawing color all the time, you can use, you can say, I'm going to import system drawing, or is it system? Yes, I'm going to import system drawing, and I'm going to say a variable of the type color, and then a boolean that is going to be display length, and then a double that is going to be size. And then here for color, I'm going to pass in the value of C. For display length, I'm going to pass the value of L, and for size, I'm going to pass the value of S. Therefore, now those values are available in the global scope, and if I run this, I don't have any problems, so that's great. So now, well, first thing, what can I do? Well, I can pass here the color. I can use the color that we have as a global variable now. So I'm going to replace this with color, and if I hit execute, you can see the arrow changes colors. And now if we just modify this, you can see how the arrow is shifting colors, and I can do it pure white now. Pop, and it just kind of disappears with my background. All right, or I can make it like super bright pink. Okay, so that is color control. Now, let's take a look at displaying the length. If you remember, in the previous video, we did something like this. We said, well, args, arguments, display, and then I want to draw text, all right? And then, was this the only option? I actually forget. Draw to the text, okay? And we did something along the lines of, what is it that I want to draw? So let's look at the arguments. So what is it that I want to draw? So the text, the color of the text, and where on the screen it was going to be showing up, and whether if, so for example, foo, and then the color, I'm going to use the same color for the arrow, and then the screen coordinate, let's say that because it's in pixel space, I'm going to say new point 2D, and it's going to be, for example, I don't know, 100 and 100. Okay, for example, and if I do that, I get an error because it takes 3 arguments. It needs another argument, which is whether if it's middle justified or not. And you can see foo here, and I can say Camp, and then it shows up there. All right, but you can see that its 2D text is static on the screen. What I want is to actually draw the text here at the tip of the arrow. So how can I do that? What I can do is, instead of drawing 2D text, there's another function that is called draw 3D text. Let's take a look at the arguments. Oh, it's a lot of stuff. So what is this? Is this, do we have all this information? Is the text, oh my God, is the text, is the color, is the plane in which we want to draw this, the font face, the bold, there's a lot of stuff. Can we make it easier? So, for example, this one could work. So let's say string, text, color, a plane, the height, and the font face. Or even this one looks also very good. The text, the color, and the plane, just that. Or the point 3D text plane origin. So this could also work. So let's prototype this, okay? So I'm going to say 3D text, and then the color is also going to be the same color, and I think it was asking for a point, correct? So what we need is the point at the tip of the arrow. So that we can find very easily by saying the point at the tip of the arrow is the anchor point plus the vector. So I'm going to do this, all right? We're going to render that. We are having some problems. What are the errors that I'm getting? So let me plug in a panel here so that we can all see the errors. The errors are invalid arguments cannot convert from string to text 3D, cannot convert from point to geometry. So it looks like I'm not working with the inputs correctly. So let me cut this out and go back to, it was text 3D. Oh yeah, because the object is a text 3D object that already contains a lot of information. So information about the 3D text. So let's try this one instead. So I'm going to do 3D text, and then color, and then text. I'm going to start with a plane in the world XY. We will change that, okay? And then height is going to be the size that I'm bringing in as an input. And then the font face, let me say Courier New, all right? For example. And because it's going to start getting complex, I'm actually going to do this where I'm going to put all the arguments one after the other. Remember, C# is not sensitive to white spaces, so you can do this. So it's working. I'm getting some 3D text. You can see that it's 3D, right? And then you can see that if I change the size of the text, it's making it bigger and smaller, but the text is showing up here on the world coordinate, and I want it here at the very tip. So improvements. So let's say before here, let's try to calculate the plane that we're going to use for drawing this text, okay? The plane is going to be for example, we're going to start with plane world XY, and then we're going to change for the plane, we're going to change the origin, and we're going to make it the anchor point plus the vector. so that the plane, instead of being here, is at the tip of the vector. If I do that, and then I remember to use actually that plane for the arguments, then we're going to get something like this, which is a 3D text that is now at the tip of the vector, which is getting closer to what I want, but I think we can do a little bit better. We can do a little bit better because what I would like to do is I would like to have the text always face the camera or face my view in a way that that it doesn't feel like it's projected on some other plane, but it's just perfectly frontal to my point of view. Now, how are we going to do that? Let me show what we're going to do with a small sketch. Okay, so let me show, I need to get the sketch set up, and because I forgot, so I need to get my laptop and plug it in. Give me a minute, I'm going to go get my laptop, bring it in and set it up so that I can draw a few sketches. Okay, I'll be right back. Okay, so let me get this set up. Let me move my coffee somewhere else. How's everyone doing? Arastu, hello, sir. Good to see you. Let me kickstart this. And okay. Are we on the same network? I guess we are. Okay, so then I'm going to put the laptop here, and I got my drawing, and then I'm going to project onto the wireless display. There you go. There you go. Oops. Did it flicker? And then I'm going to open my sketchbook, and my sketchbook should be here now. And if I do this, you should see my sketchbook. There you go. Yes, very good. Hey, Joe, good to see you again. So, how am I going to explain this? So, okay. So I have R. Oh, wait, what? I need to enable input. What is this? Okay, hold on. I need to change something in the configuration. Hello, yes. There you go. Okay. All right, it wasn't letting me input anything. So, okay, so I have X, R, G, V. Okay, and then I have my point and a vector, for example. Okay, something like this. And then what I have also is I have a camera. And let's say that my camera, for example, is somewhere here, okay? And that my camera is looking this way, right? And it has like some kind of field of view like this, right? Something like that, right? So what that means is that if I want the what that means is that that camera is also going to have some kind of plane is going to have some kind of orientation in 3D space, right? So if I want that orientation to be the same for the text, then the only thing that I need to do is basically create another plane that has the exact same orientation but a different origin, and then draw the text here on top of that text. You know, that's pretty much what we're going to do. Okay, beautiful. And perhaps I'm going to take this and I'm going to add it here. There you go. There you go. All right. Oh, wait. I should be on the other screen, correct? Oh, yeah. I should be on the other. Oh, yeah, because I'm going to be changing sides. Okay, so I'm going to copy. Can I copy this? Can I copy this and can I drop it here? Yes. And then can I turn this on and off? Oh, actually, I wanted to copy the other one. Sorry. Yep, I want to copy the other one. And this is the one that I want to copy. And this is the one that I want to drop. And now it's... And I want to turn this one off. Actually, you know what? I'm just going to stay here because otherwise I'm going to be drawing on top of the thing. Anyway, forget about that. So, all right, video mode. From a conceptual standpoint, what we have right now is something like this. We have a three-dimensional coordinate system where we have an object. This is this vector, right? And then what we also have, if you think about it, is that in order to view this vector from our Rhino viewport with this perspective, etc., kind of view, we also have this virtual object somewhere that is a camera-like object, which basically has a location in 3D space and it has like a direction, so we're looking at somewhere, and it has all these other properties, the field of view, the frustum, like all this other stuff, right? But it's basically a point, an arrow, a direction. It has like all these common geometrical properties, orientation, etc., that we are used to. So if what we want, in one of the other things that it has is that it has orientation in three-dimensional space because the camera is somewhere in the three-dimensional coordinate system and it's looking somewhere. we can very easily figure out a plane with that location and with the orientation of the camera that matches that field of view, that matches that view for the camera. So if what we want is to create text that has a frontal projection on top of that camera view that we are currently using, then basically what it's going to boil down to is as simple as creating a plane on top of where we want to draw the text, so the end of the arrow, and so the location is going to change, but the orientation of that plane, keep it exactly parallel to the orientation that we currently have for the camera the virtual camera that we're using for viewing our environment. And then as long as we use that plane to just write text, then on our camera view, that text is going to look perfectly frontal, again, because the plane that we're using is parallel to the plane that defines the camera that we're using for the view. So it's just going to be as simple as that. Now, how do we find the plane that is defining the camera? Well, we're going to use a little bit of the Rhino and the Grasshopper SDK to figure out how to get that. Let's see how to make that happen. All right. Ow. My back hurts. Okay. So remember where here we created a plane and then we manually turned it into an XY plane and we changed the orientation, blah, blah, blah. We're going to do something very, very similar. So what we're going to do is I'm going to cancel this out and I'm going to say, first of all, let me find where the plane that defines the camera is. Turns out that the arguments parameter, it contains a lot of very useful information, and some of that information relates to the viewport that we're using. So for example, I can go to the args argument and say, well, if I take a look at the viewport, there's a lot of methods that tell me where the location is, where the target is, the length, and blah, blah, blah. But something that I can do is I can get the camera frame. So the value, the plane that defines this camera. And you can see that the output is one of these out reference parameters. What that means is that the return type of this function is a Boolean. So whether if the function could get that plane or not. And the way to actually retrieve that plane is by passing it out to a plane that we predefined before and that we assign a value to as a result of the execution of this method. We have in the channel, we have a video on how to use out parameters and what they mean. A link to that video will be showing up as a card here in the corner, and there will be in the description of this video as well. So here we have that plane, and now that we have that plane, we can just use it right away. Well, we kind of forgot that that plane is actually right now on the camera, and because it's right behind the camera, we can't see it. So let's make sure that we change the origin of that plane. So we're going to say plane pl.origin is going to be equal to what we did before, the anchor plus the vector, so that the plane is at the tip of the arrow. And as I do that, what? Look at this text that is rotating with my point of view, right? How awesome is that? We can make it, we can push it a little farther away if we say, well, let me multiply the vector by 1.1 or 1.2 or something that pushes the text a little farther out. All right? Beautiful. And then the last thing we need to do is actually this text should be the length of the vector. So let me just calculate that. So double length is going to be equal to arrow dot. Can we get the length of the line? Yes, we can get the length of the line. We don't even have to do Pythagoras here. And then here I can do length dot to string. All right. However, Okay, this is going to give me like a ton of decimals. So maybe what I want to do is I want to make sure that I only display 3 decimals, for example. So let me do this manually myself. So I'm going to create a string here that is going to be the length rounded nicely. And then I'm going to use from the C# framework, I'm going to use formatting tools. So I'm going to say from the string object, the parent global string object, I want to format a string with a particular formatting. In C#, there are all these rules about how you can format decimals, money, dates. It's kind of, it's not complicated, it's just tedious. And I never remember any of this. But I know that for rounding numbers, we can do this format. So we can say, well, I want the value to just have 3 decimal parts. So if I use this string as the template that defines that formatting, then whatever value I pass now, so for example length, will be formatted with these 3 decimals. Okay? And again, I know this because I basically Googled it out before doing this exercise, but there's a lot of documentation on how you can properly format strings, etc., etc. That's actually something that varies very strongly depending on different languages. So this is a very C# way of doing that. And then here, instead of that, I'm just going to output that manually rounded number that I have generated. Okay? I can control the size, so I can make this value bigger or smaller. And I also would like to make sure that this on and off turns off the visualization or not. So then I guess that's going to be just as easy as saying if display text, display length, then do all this stuff that we just designed. Otherwise, don't do it. Okay, otherwise just skip that part. So if I now turn this false, no text is displayed. And if I turn it on, this text is displayed. Woohoo! So we have a bit more of an enhanced vector display visualization than the one that comes out of the box with Grasshopper. All right, we could get some inspiration from the actual Grasshopper component because this one also, for example, this one takes the color. We've done that already. This one also takes the width of the vectors line, so how thick the line is. We could do that as well. But I'm actually going to leave that to you, the viewer, as an exercise if you want to practice adding more parameters here. Okay, because I would like to move on to the next component, which is going to be, I forget, well, let's move on to the next component, whatever that was on my list. Alrighty, how was that? How are we feeling? I'm going to add this to the group. There you go. Beautiful. Okay, so what is next? Oh, a component that takes a curve and visualizes the curvature. Okay, so for that, okay, we did this last time. How did we find the curvature? How did we draw the curvature graph of this curve? Can someone please remind me? Curvature graph. There you go. Okay. Okay. Curve hair is going to be blue, for example, whatever. And then the way we did that was we took a curve. Okay, so we're going to copy and paste this. I'm going to copy my notes here to the side. Okay, and then I'm going to remove all of this here. We're probably going to start like this. Okay, and then that's going to be this. and this. So these are going to be here, and these are going to be, you see my OCD is killing me again. All right, and here, and this is actually going to be extremely easy, really. Okay, my coffee. Yes, I forgot. What I wanted to do was to show you how to draw the curvature graph of a curve using also Grasshopper previous pre-visualization. What does that mean? What it means is, I don't know if you're familiar with this, but you can, if you draw a curve in Rhino, for example, let me turn off all this vector stuff. If you draw a curve in Rhino, for example, in Rhino, there is this component or this action that is called curvature graph, which if I choose it on this curve and I crank up the scale a little bit, what it does is that it draws this diagram on top of the curve that is a visual representation of the curvature of this curve. The curvature is basically the inverse of the radius that you would need for a circle to mimic the curvature of that curve at that particular point. So you can see that when the circle that we would need to be tangent to these points is very large, then the curvature is actually very small. But you can see how as the curve becomes more curvy, if you will, this value increases. The curve is very curvy here, so the curvature is very high, right? Then the curve is almost straight here, so the curvature is very small, and then it goes higher here, right? And you can see that there's actually jumps in the rate at which the curvature is changing based on the control points of the curve. So you can see this is actually quite interesting. So you can see how where the control points for this NURBS curve that I just drew, where the control polygon hits the curve, so at the middle of here, there's actually jumps in the curvature for reasons that I have explained in other videos about how NURBS curves work, etc., etc. But displaying this as an analysis is actually quite interesting. And in Grasshopper, is actually super easy to do. So you can see that this panel asks me for a few data. So the scale of the display, the density, the color of the graph. So I have mimicked all of that in this C# script component where I'm going to be input in a curve right here. Then I have a color for the display of this curve. And then I have, I forget what was this, like the size of the, I have it here somewhere. S is going to be the scale of the hair. HD is going to be the density of the hair. And then SD is going to be the density of the samples. All right. And I've already done what we discussed in previous videos. I have created global variables in the scope of this component and that I'm using to store copies of the input information that we are bringing in here. Okay, so very simple. So how are we going to do this? It's going to be the simplest of all the exercises. I'm going to add the overrides here, and then what I'm going to do is, first of all, I'm going to go all the way to arguments here where we draw viewport wires, and then I'm going to say arguments, display, and I'm going to say draw. Literally, there is draw curvature graph. There's literally a function that does this all for us. We could do it manually. We could find the curvature, draw the curves, draw the line. It would be a fantastic exercise on how to do that manually. But I'm actually going to leave that to you and the viewer to do that on your own, okay? Because it's not so straightforward. It would probably deserve its own video. So I'm going to draw the curvature graph, and I'm going to go through the overloads, and I can see that there's already one that has the curve, the color, and all the properties. So I'm just going to go straight into it. So curve is going to be the curve that I want to draw. Color is going to be the color. Then the hair scale. Then this is going to be the hair density. and then it's going to be the sample density. And if I don't have, you see that I had a typo already. If there's no typos on my end, this should already be working. So I'm going to turn the previsualization. Oh, and something is showing up. So let me crank down the scale and let me up the hair density. And the sample density is not doing anything for some reason. I don't know why it's that important. Anyway, but you can see that I'm already getting the graph as expected. Okay. So that one was just a one-off. That was so simple. We have to remember though that in the bounding box, we have to make sure that we at least include the curve. So we need to say this should at least include get a bounding box, and we don't need an accurate bounding box, so we can do false. And then we just do that to make sure that the viewport is not going to clip out parts of the curve. All right. Beautiful. So that was great. Now, this works, this curvature graph system, this works for curves, but you can also analyze the curvature of surfaces, right? And that's actually much more interesting and also a bit more complex to implement. So how about we try ourselves to create a component that does that displays with colors the curvature of a surface. But first, before we do that, let's actually take a closer look at what displaying the curvature of a surface actually means. Beautiful. Okay. Click save as preview components. Okay. And I'm going to open another Rhino here on my side, and then I'm going to use that Rhino to open the other file that I had going on and to get that surface that I already used. That was pretty nice. So I'm going to take these curves, I'm going to paste them here in Rhino. I'm going to scale them down by 0.1 to make a smaller surface, and I'm going to move them here. Okay. And before I start blabbing like I typically do, I'm going to loft this. Yep, normal, and then I'm going to say curvature analysis. There you go. Gaussian curvature, mean curvature, minimum radius, maximum radius, Gaussian, etc. Okay, so I'm going to show this. Outer range. Nope. Yep. Okay, I guess that's what it is. Okay. So how am I going to explain this? Hide this. In Grasshopper, I'm also going to stop this exactly. Hey Andres, hola. Richard, what's up? Okay, so I'm going to now explain the surface by creating a surface and then explaining curvature. We're going to take a look at Gaussian, we're going to take a look at mean, and I'm probably going to explain overall what are we going to do, the technique that we're going to follow in order to, should I draw in order to do that? I probably want to draw something, right? Yeah, let's draw something. And so what I'm going to do is I'm going to have a surface like this and like this something. I'm going to draw this, well, and here as well, obviously. Okay. And then we calculate the value for each one of those. And then what we do is that in order to display that, we create a mesh. We create a mesh between those, and then we use, for each one, we apply vertex colors. So that it now shows up with colors. That's what we're going to do. Okay, I think we're ready for this. Let me first create a surface, the one that we're going to be working with and analyzing the curvature on. In order to do that, I'm going to do this surface where I'm going to loft a few curves to create the surface, but the first few ones are going to be basically straight lines. And I want this because I want to make sure that this area of the surface is as flat as possible so that it has very little curvature. But then I want this other area to have a lot of curvature so that I can see the contrast between this. So that's why I'm going to be lofting a surface between these 5 straight lines and then this really curvy one here. So I'm going to say loft, and between this one, this one, this one, this one, and you see, and then you can see how this area is, you see there's still like a little bit of a valley here and a top here, but it's almost flat, right? Whereas compared to this one here, that has a lot of curvature. So if I take this surface and now I type curvature analysis, what you can see is that I get this thing here. I get this color representation that tells me which areas of the surface have more curvature and which areas have the least, right? And you can see that curvature in this case is the Gaussian curvature. The Gaussian curvature, we haven't seen that in the channel yet, but it's basically a measure of how concave or how convex a surface is. And when it approaches 0, it's basically very flat. So you can see how this area has almost close to 0 curvature. And you can see how the sides of these hills are also pretty flat, which is kind of interesting. But you can see how the red areas are areas that are very concave, so it has positive curvature in both directions, whereas the blue areas are areas that are very saddle-like. So it has negative Gaussian curvature, so those areas have positive curvature in one direction and negative curvature in the other one. I used to have a video about this, but I don't have it anymore. So maybe I will make a video at some point anyway. I can set auto range here, and then you can see that the values get a little adjusted. Now I get to see it a little less. I don't like this actually. Let me go back to 0.02 and minus 0.02 as a range, all right? Or I could also take a look at the mean curvature. The mean curvature is basically the average of the curvatures in the two principal directions of that surface. And if I do auto range, you can see that this also tells me that this area is pretty flat. These areas on the sides are pretty flat, and then these areas, these areas are actually increasingly curvy. All right. So what I would like to do is I would like to have a component that generates something like this. It generates a visualization that tells me either mean curvature or Gaussian curvature. I don't know how we're going to do that, but it tells me, it gives me an indication of how curvy a surface is. And the way we're going to do that is we're going to follow a technique that is going to be called, I forget what the real name is. I think it's called a false color mesh. What that means is that many graphical environments cannot really color surfaces, and that's particularly true for NURBS geometry. So in order to get this kind of pre-visualizations, what the environments do is that under the hood, behind the scenes, what they do is that they turn this surface into a mesh. So let me show you here. What they do is that they take the surface, and under the hood, they turn that surface into a mesh by basically populating the surface with points at regular intervals, and then creating a mesh through all those points. And then what they do is that to every vertex of that mesh, they assign a color value that corresponds to whatever you are trying to represent. Okay, so in this case, curvature. And then we choose colors based on curvature. So maybe for zero curvature, we choose black. And for full curvature, whatever that means, we choose white. Or we choose these nice color gradients as you were seeing before in Rhino. But that is because many graphical environments have a capacity to display meshes that have false color information. I don't think that's the right term, actually. I think I might be making this up. But they have like false color information embedded in the vertices of that mesh. And Rhino happens to be one of those environments. So what we will need to do for this is we will need to take a surface as an input. We will need to create a mesh at regular intervals somehow in that mesh, in that surface. And then for each one of the vertices, calculate the closest point on the surface to that vertex, calculate the curvature on that surface at that point, and then turn that curvature value into a color that we attach to the mesh. All right, that sounds like a lot, and so let's take a look at how would we do that code-wise. All right, let's do that actually. So where's Grasshopper? Okay, and then I'm going to go to the So I guess this is okay, so I'm going to copy all of this so that I don't forget. I'm going to have a cheat sheet here, and I will need to remind myself of something. Okay, so, and what were we doing? We were I'm going to output in the mesh. So I'm going to do the exercise in a way where I'm going to be creating the mesh. I'm going to output the mesh anyway in Grasshopper so that it's a bit more tangible. We can see it better. And I'm going to be outputting also values for the curvature. And once we have all of that working, then I am going to draw the mesh with the false colors technique. Okay. Yeah, which we don't need. We don't really need any of these or any of these. Okay, so let me then prepare the exercise. The exercise is going to be this. It's going to be vector preview. This one is going to be what? Curvature preview. This one is going to be a curvature graph. And then this one is going to be surface curvature graph. All right. And then we're going to bring in the surface. We're going to bring in the surface. I'm going to fill all of this. And I'm going to remove all of this. Okay, and the surface is going to be here. And I'm going to have some outputs here. Okay, so that's looking good. And I'm going to take a 1 minute break and then we're going to get hands-on. I'll be right back. Give me a second. Okay, we're back. Okay. No, Daniel Shipman is streaming right now. Why do we always overlap? Why? I thought he was streaming on Saturdays. Ah, that sucks. Oh boy, I'm getting a notification. Daniel Shipman, Nature of Code. You should definitely check him out. If I were you, I would be on the other. I would be at the coding train probably. All right, where were we? Yes, we were about to. Start with this. And then, and then, and then first we're going to create the mesh. Okay. So I have kickstarted this exercise by creating a C# script component that takes a surface and that takes a double value that I will explain very soon what we're going to be using it for. Okay. And then I'm just going to basically choose the surface here that I want to do, right? And then I'm going to go into the component, and then I just wrote here, this is very useful when you write algorithms that are going to be longer or that are a bit more complex, to write yourself what's called pseudocode, or like at least a roadmap of what are the things that you want to do. So in our case, in order to achieve this global visualization, what I would like to do is I would first, as I explained, what we're going to do is we're going to generate a mesh that is going to be derived from the surface. And it's going to be a grid mesh. I'm going to call it a grid mesh because it's going to be regular in the two directions. I want to do that because I want to sample my surface at as regular intervals as possible. So if I make like a messy triangular surface, that would also work, but typically we follow this because it's a bit more regular, and you have regular. I don't even know why at this point, but I guess random triangles would also work. But I think this regularities has value when we do these things. Anyway, for each vertex, then of the mesh, what we're going to do is we're going to compute the curvature value of the surface. So we're going to find the closest point to that mesh vertex on the surface. We're going to compute the curvature at that point. And then once we have the curvature of all the vertices, what I'm going to do is I'm going to convert that curvature to a color value that we can attach to the mesh so that we can visualize that. All right? It's going to be a bit more involved than the previous exercises. So in order to make sure that we get a good grasp of what is going on at each step, I'm going to be using the output parameters A and B to output temporary information about this. And maybe I actually may leave that information out there. Why not? Actually, I'm just going to do that right now. I'm just going to say mesh is going to be the mesh that I want to create, and C is going to be the curvature values. All right. So let's just stick to that. I kind of like that idea. So first of all, we need to generate a mesh that is derived from the surface. The way I would do that, if we had enough time and if I didn't want this video to take 3 hours, it would be to manually generate combinations of UV parameters on the surface, then find the point for that UV coordinate on the surface, and then manually recreate a mesh joining point 1, point 2, point 14, point 13, etc., etc. That will ensure that the mesh has this regularity that I like, but it's a little bit of a tedious process. It's just long to write. It's not difficult, it's just tedious to write. So what I'm going to do is I'm going to use a shortcut, and then I'm going to use Rhino's surface to mesh methods that give me already meshes that give me already meshes from a surface with a few minimal parameters. Okay, so how would I do that? So what I could do is, first of all, I'm going to create a global mesh. All right, so mesh, I'm not going to care about that yet so far. So I'm going to create a mesh, and I'm going to say, I'm going to use from the mesh object, I'm going to say create from surface. All right, the surface that I want to use is going to be this one. All right, and if I gave it no parameters, then Rhino would make whatever decisions to create that mesh in whichever form. So let's say that I want to now take a look at that mesh. So I'm going to output it through the M parameter, okay? and you can see that I get whatever mesh. All right. And if I render that mesh here, and I hide my surface, I hide my curves, and I actually display here that I want to preview the mesh. So if I go to display, preview mesh edges, you can see that I now have this representation of the mesh. Now, this doesn't look great to me. First of all, because the intervals between vertices are not so regular. So I have many more vertices in this direction than I have in this other direction. And that is because Rhino is actually optimizing this meshing to create big triangles where the surface is actually pretty flat, as opposed to creating tiny triangles where the surface is very curvy and then I need more definition. It's actually a very smart meshing, it's a very optimal one, but it's not the one I want. I want something that it's a bit more organized, a bit more grid-like. I could use this, no problem, but I'm going to try to find a mesh that is a bit more quad faces at regular intervals. And I'm also going to do that because I actually want to use that same technique for the last component that we're going to do in this video. So how am I going to do that? Well, if you look at the create mesh surface, it has two overloads. One of them is just the surface and then whatever parameters. And then another one is this one that takes an object called meshing parameters. Meshing parameters is an object that contains information about what are the parameters that we can tweak and we want to control specifically for the creation of that mesh. So what we're going to do is, first of all, I'm going to create a meshing parameters object that I'm going to initialize to meshing parameters. I'm going to initialize to a default set of values. So you can see that Rhino gives me already a few presets, if you will. I can choose a coarse mesh, a default mesh. That's probably what this was doing already. I can do a fast render mesh, quality render mesh, smooth mesh, or the one that I'm going to choose, which is a minimal one. All right. Then this, if I were to print this, I wonder if this is going to show any values. So if I were to print this to the console, yeah, I don't get the values. So I don't know what values there are there. But if I were to use that now as the meshing parameters here, you can see that the meshing that I get is actually quite different, right? So first of all, it's made out of quads, which I like because, again, because of the exercise that we're going to do last in this video. Yet still has the problem of having many more vertices in this direction than it has in this other direction. So I would like to control that, and I would like to change some of the default parameters that come with this. So for example, MP, if I do dot, you can see that I can actually access the values of grid angle, maximum count, minimum edge length, etc., tolerance, all those things that already have some presets. So what I'm going to do is I'm going to change the grid aspect ratio, and I'm going to ask it to make it as close to 1 as possible. And then here I'm going to say the maximum edge length must be this value that I input in the component, so that I can choose a more refined mesh or a less refined mesh when I define my visualization. And for the minimum, I'm also going to do the same thing because I want Rhino to give me as square faces as possible. So what I'm going to do that now, now I have this like really oversimplified mesh. This is a little too much, but if I now crank this value down, I believe that I can get a more, you see how beautiful is this? How it's not exactly, you see, it's still doing some optimization, but it's much better than what I had before, right? So I'm going to keep it at a value of 2, for example, or maybe a value of 1. A value of 1 is going to work. 1.5. Not too much, not too little, all right? Beautiful. So the mesh is looking great now. So I have a mesh that I'm happy about. So the next thing that we're going to do is for each vertex of my mesh, I need to compute the curvature value on the surface. How am I going to do that? Well, what I'm going to do is I'm going to write a for loop. I'm going to iterate over all the vertices in the mesh that I created. I'm going to find the closest point on the surface, and then I'm going to measure the curvature on that surface. So I'm going to say for int I equals 0, so I'm going to, just to make sure that we're on the same page, I'm going to do here for each vertex, compute the vertex. I'm going to say I is going to be less than the amount of vertices, in the mesh. Okay, that's one thing. And then what I'm going to do here is I'm going to say, well, first of all, I'm going to get the vertex. So I'm going to say 0.3f. I'm going to explain why in a second. V is going to be mesh.vertices. And then you see how when I open the square bracket to use the index, the return value is giving me a 0.3f. Turns out that meshes have points with 3 float values instead of 3 double values. That's because you don't really need so much precision to store the coordinates of vertices. So we use float points, which have half the memory footprint of double points, so of double values. So I'm going to take the vertex there, all right? I'm actually going to rename this vertex. And then the next thing I'm going to do is, now that I have the vertex, I want to find the closest point on the surface. So I want to say surface, I want to find the closest point on the surface, and I can give it a test point that's going to be the vertex. And you can see that the output is not a point. The return of this method is a Boolean, whether if it could compute this point or not, but I have to use out parameters to store the UV coordinate of that point. So I'm going to do out U, out V, and I'm going to predefine those here as 2 double values. All right. And then I'm going to find, excuse me, and then I could find the point, but I won't really need it because as soon as I find as soon as I do curvature at doesn't ask me for a point. It asks me for the UV coordinates of where do I want to find the curvature. So that's going to be U and that's going to be V. I want you to look at how the return value of this method is an object called surface curvature. It's not a number because there are many different curvatures. There's Gaussian curvature, mean curvature, etc., etc. So what Rhino does is that it bundles all that information into an object that has all that information and that we can read from. So what I'm going to do then is I'm going to say, well, surface curvature SC is going to be equal to this value. All right. And then from SC, I can probably read the Gaussian curvature, that is a number, the mean curvature, that is a number, the normal to the surface, that's a vector, the osculating circle, the point, the kappa. There's like a lot of interesting stuff that is bundled in this object, all right? So for the time being, let's say that we're going to choose curvature, the Gaussian curvature, right? So that would be something like this. It would be, that's the value that we will want to represent, okay? Maybe we can add some Boolean to the component, like you want Gaussian or you want mean curvature or something like that. We're not going to do that. I'm going to leave that for you, the viewer. But let's say we want to represent the Gaussian curvature, all right? We can read it, but what I would like to do is actually store it somewhere so that I can use that value later on to compute the color. So then what I'm going to do is, first of all, before I forget, I'm just going to create an array here of curvatures, which I'm going to initialize to how many elements. I want to store as many curvatures as vertices I have in my mesh. So that's going to be mesh.vertices.count. All right. And then what I can do now is in the curvatures array at position I can store the Gaussian curvature of this surface. All right. And to just make sure that we see what's going on, can I output those curvatures over the C output? So let me just do that. the curvatures, I'm going to output them, and you can see that, boom, I have like a lot of zero curvatures. That's probably these vertices here. But then as I scroll down, I start getting like tiny values, which start becoming larger and larger and larger. And actually, I could use, for example, a list, not list, a range component, and to analyze the bounds. So if I pass in this list, this component is going to give me, what is the minimum and what is the maximum of that full list. You can see the minimum is minus 0.25, and the maximum is 0.16. All right. Beautiful. Now, how do we turn this into actual colors that live on this surface? Well, let's say we're going to keep it easy. All right. And then what we're going to do is we're going to, for example, we're going to say that the surface will have a black color wherever the Gaussian curvature is minimum. All right. And it's going to have a white color wherever the Gaussian curvature is maximum. Actually, you know what? I'm going to switch to mean curvature because, yeah, I'm going to switch to mean curvature instead. So, well, actually, let me think about what I'm going to do. Give me a second. What are we doing? Are we doing Gaussian or are we doing mean curvature? What are we doing? What shall we do? We're going to stick to Gaussian, but I just don't like the fact that we're going to reduce. That's just not very clean. That is not very clean. But anyway, I think we're going to stick to Gaussian. And then we're going to leave that as an exercise for the viewer. So, sorry, I just thought through it. We're going to go back to Gaussian, and I will explain later why was I thinking about this. Anyway, so what I would like to do is I would like to use some kind of rule, as in I'm going to draw black color whatever the minimum Gaussian curvature is, and I'm going to draw white or red or green or some other color, whatever the maximum Gaussian curvature is. In order to do that, first of all, I need to compute where the minimum and the maximum are. So I can do that as I am calculating the curvature values. What I can say is I'm going to define a variable called minimum, which is going to be where I store the minimum value of this curvature, which I'm going to initialize to a really large value. I can do that by just from the double object, just getting whichever the maximum value it can store, and I can do something similar for the max. So this I can initialize to the smallest possible value that a double number can take. And then during my for loop, every time I figure out the Gaussian curvature, what I can do is I can say if sc.Gaussian is greater than the maximum, then make the maximum that value. And similarly, if sc.Gaussian is less than the minimum value that we have found so far, make that minimum value that Gaussian curvature that we have found. If we do that, then we can now print to the console minimum.toString, and then, for example, maximum.toString to figure out if the two values are the same. We can see that, yes, the minimum matches what Grasshopper is telling us. The maximum also matches that. With this, it's great because now we have a range. We know where the minimum value is and where the maximum value is, and we can create a color that is an interpolation of those two values. How are we going to do that? Well, I'm going to say that I'm going to store, how are we going to do this? I'm going to store in a new variable. I'm going to store, well, let me think about this. Okay, yes. So let's do this first. What we're going to do is we're going to take all the curvature values and we're going to normalize them. Normalizing them, you may have seen in other videos, is a process where you take a collection of numbers, you look at the ranges, and then what you do is you modify those numbers to make sure that the whole collection of numbers has a range of values that goes from 0 to 1. So what I'm going to do is I'm going to proportionally change all these curvature values so that instead of going from -25 to 0.16, they all go from 0 to 1. And this is an operation that is extremely common because having a collection of numbers from 0 to 1 then makes it very easy to translate to other domains, such as, for example, a color range between 0 and 255. So I'm going to normalize those values. So what I'm going to do first here is I'm going to create a value, an array called normalized values that is going to be going to have the same size as the previous. Okay. And I'm also going to calculate the range, the difference between the minimum and the maximum. So that's going to be, the difference is going to be the maximum value minus the minimum value that we have calculated so far. And now I'm going to iterate over all the elements. I is less than norm dot length, and then I plus plus, and then for each curvature value, so double C is going to be curvature at that point. For each curvature value, I'm going to normalize them. Normalizing it means dividing the value that we have by the range in which it is, offset by the minimum value. I'm going to say double n is going to be equal to the value of the curvature minus its minimum, and then divided by the total range. I have explained this in some other videos. A card might be showing up somewhere, or maybe not, I forget, but it's a very common operation. You can also Google that out there. And then once we have that, I just want to store that in the array. Norm is going to be equal to that value, that normalized value. Beautiful. Just to make sure, I'm going to output here an n value, and then I'm going to output that normalized. So that's going to be equal to normalize the array, and then there's an error here, and then that's probably curvatures. Exactly, that's the error. Beautiful. So let's see if this is actually working. So I'm going to copy this and say normalized. And then you can see that this now has values of 0. It has values of 0.61, whatever. But if I plug that into the bounds, you can see that the whole list has values between 0 and 1, which is great. It's very useful, as we're going to see very soon. Okay? Beautiful. And then last but not least, what I want to do now is I want to go over all the vertex colors, and then over all the vertices, and add a color to the mesh that corresponds to this normalized value. How am I going to do that? Well, first of all, let me iterate over all the vertices of the mesh. I is less than mesh.vertices.count, and then I plus plus. All right. And then what I'm going to do is, first of all, let me get the normalized value we have calculated before. So that's going to be norm.y. Then what I'm going to do is I'm going to multiply this value by 255. So that instead of 0 to 1, it's now 0 to 255. So double color is going to be equal to n to 255 times n. What that means is that now I know that that value has a color that is going to be between 0 and 255. Now, something that I need to do is I need to make sure, because when I use colors in graphic environments, colors, if they are represented between 0 and 255, they don't have decimal part. So I need to make sure that this is actually an integer, which I can cast like this, and then I can change this value to this color. All right? And then, once I have that, I can use that either as the red channel or the green channel or the blue channel or the 3 channels of a color that I'm going to add to the vertex colors of the mesh. So I have the mesh and I can say, can I add to the vertex colors, which right now is empty, can I add a new color? And that color is going to be 3 RGBs. So because I already have, and you can see how they're integers, sorry, I keep mispronouncing that. So let's work only with the red channel right now. So I'm going to say color 0, 0, all right? And actually, I think that's it, right? So let me run this. Oh, error, what's going on? Cannot implicitly convert 104. Cannot convert from, oh yeah, because I need to do parentheses to convert the whole thing. All right, and what? What is going on here? Nice. So you can see how now I have a brighter red in the areas that have the most positive curvature. I have a medium red in the areas that are flat, and I have a black in the areas that are the most negative curvature. All right. This is the part that I was not very happy about, because if you think about it, Gaussian curvature is 0 wherever things are very flat, and Gaussian curvature is positive where things are very concave and is negative where things are saddle-like. So for Gaussian curvature, it would have made a bit more sense to have full black wherever things are very flat, and to have full red wherever things are very positive, and to have full some other color where things are very negative. Wait, can we change this? Can we change this in a way that we can make this happen? I think I want to make this happen because I don't really like this. It should be black where it's 0, and it should be okay. All right, I think we're going to do this. Yep. I think we're going to do this. Okay, we are going to do this. Hope this works out because I haven't prepared for this. But the fact that we're not getting black where the Gaussian curvature is 0 is actually annoying me tremendously, because I find it a very non-rigorous approach to displaying curvature. So how are we going to change things to make this happen? Well, we're going to try the approach of using red color for positive Gaussian curvature, that is when things are very concave like this, and to use a different color like green, for example, when things are saddle-like, and when they approach to 0, we're going to use black. Okay, what does that mean? What it means is that instead of normalizing the whole thing, all the negative values and all the positive values to a scale of 0 to 1, which means that the midpoint 0 falls somewhere, in this case like around 0.61, which is not very rigorous. What I'm going to do is I'm going to change the normalization rule so that this whole domain from -25 to +16 becomes a domain that goes from -1 to +1, so that we know that values that have originally 0, they stay at 0. Values that have -25, they become -1. And then values that have +25, because it's bigger, we need to keep the scale the same in both directions, they also get a value of +1. Let's take a look at how would we change that. It's going to be actually quite easy. What we're going to do here is we're going to say, instead of the difference, which we don't really care that much actually, we're going to call this the range. And the range, what we're going to do is we're going to take the maximum value of the two ends. So we're going to say, well, I'm going to choose if 0.16 is bigger than -25 in absolute terms, then I'm going to take whichever one of those two. So I'm going to say math, I'm going to take the maximum value of both math, the absolute value of the minimum, and math, the absolute value of the maximum. All right, so that's going to be the range. And let me comment all of this out because it's going to fail, and let me print the range to the output to see that it's working. If I do this and I print the range should be +25, which is what I was expecting. All right. Then for the normalization, I'm going to change the rule, and I'm going to say, well, instead of doing this, what I'm going to say is that the normalization is going to be the value that we have for curvature divided by that range. As simple as that. All right. And it's going to remain positive or it's going to remain negative. And if I do that, oops, something just happened here. The array length, line 94, normalization length. Well, why was this not? Okay. Okay. And I'm going to look now at the normalized values, and you can see that wherever the Gaussian curvature was 0, now it stays 0. And now wherever it had a tiny negative value, now we still have a tiny negative value, etc., etc. And if we look at the bounds, we can see that now it goes from -1 to 0.62, which is good. It's great because since the other end, the positive end, doesn't have the same scale, we want to cap it at whatever the maximum value is. And then for the colors, I'm going to follow the following rule. What I'm going to do is I'm going to say, well, I'm going to get the normalized value. And then if, okay, where was I? Yes, I'm going to say, if the positive value is greater or equal to 0, then what I'm going to do is I'm going to use the red channel. So what I'm going to do is I'm going to say color is going to be equal to what I did before, int of 255 times n. All right. And then I'm going to the mesh vertex, to the vertex colors, I'm going to add a new color, which is going to be this on the red channel, 0 and 0. All right. And if this is equal to 0, this is also going to be equal to 0, which is going to give me black, which is absolutely fine. Otherwise, if it's not greater than 0, then I'm going to use a very similar thing. But because colors cannot be negative, I'm going to multiply by -255. Because this will be negative, the color will become positive, and then I can use it now. But instead of using it in the red channel, I'm going to use it, for example, in the green channel. Are you ready for this? Is this happening? Boom! What? There you go. This looks so much better now. So let me turn this on. So this looks so much better now because now the flat areas are very dark, almost black. They should be black actually. And then the saddle like areas, the areas with negative Gaussian curvature are greenish, and the areas with positive Gaussian curvature are red, you know? And you can see that because of the scale of all this geometry, this area is much brighter because it has greater negative value than this area, which is not so red bright because, as we saw, the absolute value of the positive curvature is less. All right. If I crank up the size of the mesh, then you can see that we can see things a little clearer. All right. And I'm kind of not very happy with the blue lines or whatever, but you can see that the color distribution changes a little bit because now here, look at this, it's actually quite interesting. The range changed because I just happen to be hitting points here that have a very, very strong positive curvature as opposed to these ones here. That is actually quite interesting. So you can see how the definition of the mesh and where the vertex points land on the surface actually makes a big deal of a difference, you know, this point. So a very fine mesh, I guess, would make, you see, that is actually quite interesting. Beautiful. So, okay, so now you have the mesh, and I'm actually going to keep all these values outside, perhaps not the negative one, but yes. So we have now a way to pre-visualize, and if I were to turn off the mesh edges, now we can clearly see that the colors of the mesh as the pre-visualization. All right, this is a very, very common technique that is very commonly used for displaying data that is associated to a surface. When you do solar analysis and that kind of stuff, this is also the technique that is used. And actually, we have a video somewhere on a playlist about using meshes to display color information, such as, for example, solar analysis. There will be a card popping up somewhere here in the corner and in the description of this video. All right? Beautiful. And if this wasn't enough, can we move on to the last example that I want to do in this exercise, which is going to be taking a mesh, for example, the mesh that we generated in this component, and then analyzing the planarity of the faces of that mesh and rendering that also as mesh colors. Wait. Actually, we haven't actually rendered the mesh. What? We're outputting the mesh? But because we're outputting the mesh, oh yeah, we haven't actually rendered the mesh. Oh, that was terrible. Okay, sorry. Let's actually render the mesh, because now look at what's happening. If I were to cancel out the outputs, if I were not to output nothing here, then this component is not pre-visualizing anything. You see, if it was just pre-visualization, I wouldn't be seeing anything. So I need to actually add that to the code. So how are we going to do that? We're going to add the overrides. We're going to add the floating global render mesh, for example. I'm going to call this here. And then I'm going to also make sure that after all these calculations, I pass the mesh with the false colors to the renderer. All right. And now, remember, we were using draw viewport wires for geometry that is linear. The whole point of this exercise was actually to use the other method. It just took us 45 minutes to build all the code, but now that we have the mesh with the false vertex colors, now we can say arguments, display, draw mesh with false colors. It's just as simple as that. And I'm going to use here the render mesh. Okay. And if I run this, we do see the exact same thing. But if I were to not output anything, right, then this component, I turn it on and off. You can see that the native pre-visualization of this component is the mesh with the rendered, with the colors. And something that I need to not forget to do, okay, something that I need to not forget to do is to make sure that I properly pass a bounding box so that the whole mesh always stays within the clipping area of my rendering. So that is just as simple as render mesh dot get bounding box, and because I don't really need precision, I can do false and make the operation cheaper. And just for the sake of it, I'm going to still output the mesh, and I'm going to output the curvatures, and I don't need the normalized values probably. Oh, I can, yeah, why not? The normalized values, yes. It's kind of interesting. All right. Beautiful, very beautiful. Okay, so here we go. Color, false color, mesh technique for rendering curvature, for example. Let's move on to the last example where we're going to do a similar thing, but we're going to render the mesh with colors that correspond to the, the planarity of the faces of a mesh. Nicolas! Thank you, thank you. That means a lot to me. All right, so we have this. Okay, so I'm going to group this whole thing together, and I'm going to take a mesh that I'm going to bring in from here. Okay, I'm going to take that mesh. Can I render? Can I display it with the custom previews? Okay. All right. I'm going to take that mesh, and then let me look at the example that I did when we were preparing this exercise, and yeah, and let me put it right here. Oh boy. All right, how am I going to explain this? Oh, it's going to be... Actually, what I don't need to do is I don't need to mesh this thing anymore. I can take a mesh instead. Yeah, I guess we can do that. So here I can just right click and just do a mesh here, and this is going to be of the type, oops, I don't know what's going on. I'm going to make this a mesh object, and I'm going to remove this because we don't need it. And then maybe I want to output planarity values here. Why not? And maybe normalized values. Why not as well? And I'm going to take the mesh in there. All right. And then mesh face planarity. Planarity, for example. All right. How am we going to do that? And I'm going to remove all of this. And this doesn't apply. Wait. Yes. And we're going to remove everything. And I'm going to add, what is going to be a compute planarity for each face. And for each face, that's going to be the first step. Then we're going to normalize them. We're going to normalize them. And then once we normalize them, we're going to render each face as a single mesh with vertex colors. All right, so let me explain how that is going to work. Or do I need to explain that now? I can explain it later when we get to that part, probably. Yeah, we can probably take a look at that later. All right, let's get busy. And for that, I think I'm going to need to draw a little bit. And so I'm going to make a new sketch here before closing. Yes. There is even more on Discord. You crazy folks. All right. So let's say I have a face. I have a face, and the face is like something like this. Okay, I have a vertex, I have a vertex, I have another vertex, and I have a vertex. All right, something like that. And the face is something like this. It's a quad face. We're only going to do this for quads because triangles are always planar, all right? So we have that. And then what we kind of want to do here is actually, let me do darker gray here. Actually, let me do that on a separate layer in case I want to turn this off. All right, and then in the next layer, what I actually want to do is I want to turn this off. I want to actually say, well, oops, do you see that? Oh yeah, okay. In the plane that is formed by these two, there is this one is off plane. So what I want to calculate is actually this distance, what I'm going to call the offset. All right, so that's what I want to calculate. So how am I going to do that? Well, I'm going to be super easy. So what I'm going to do is I'm going to create a vector going this way. I'm going to create another vector this way, and then I'm going to calculate the cross product. And the cross product is going to give me a vector that is perpendicular to the two. All right. And then after that, I'm going to create another vector that is going to be this vector here. And what I want to do is I want to project that vector. I want to project that vector here, create a vector like this, and that vector, and then calculate the length. And that's what will give me that offset. So once I have that offset, then I can calculate. Yep. All right, so let me explain that. But I need to start from here because I haven't really, no, I need to start from here. No, from here, because I haven't really done anything yet. Yes, okay. Oh, and I need to start probably writing code, and then for each one of them, I want to explain this as soon as I want to calculate the planarity of that face. Mm-hmm. Mm-hmm. Okay. All right. I think we're good. Let's get started. Oh. So building on the same mesh that we have output in the component before, I have created, I'm just taking the mesh, and at this point the colors that it has, I don't really care about them at all. I could actually write a component to clear the vertex colors of a mesh. That could actually be interesting and super easy to do, but you can probably do that as a viewer. So what I created was this C# script that takes a mesh, and what I would like to do is to show as a preview with a set of colors the planarity of the faces in this mesh. So what I'm going to do is I studied this component already that takes the mesh. It has these two outputs, P, which is going to be the values of planarity, right? And then N, which we're going to use similar to what we did before, which is going to be the normalized values that we're going to output throughout the process. And then in order to get this done, the first thing that we're going to do is for each face in the mesh, we need to compute the planarity. Planarity is not a it's not like a Gaussian curvature that is very clearly defined. Planarity can be defined as whatever we want to define it as. And one of the easiest and best ways of defining planarity is if you have 4 points measuring the offset of one of those points from the base plane that the other 3 form. I'm going to explain how that works, but let's start by building the scaffold, which is going to be, I'm going to create an array that is going to be called offsets, all right, and I will explain in a second, and I'm going to initialize it to the amount of faces that we have in the mesh. So that's going to be m dot faces dot count, length count, exactly, all right. Then what I would like to do is I'm going to iterate over all the faces. I is less than 0, I is less than m dot faces dot count, and then I plus plus, and then for each one of the faces, I would like to calculate as a value, I would like to calculate the offset. All right. And for this, because it's going to be a fairly involved operation, I'm actually going to create myself a method to calculate this. I'm going to call it planarity. I don't have it yet, but I'm just designing what it would look like. So for this, I would probably want to give it the mesh. I would probably going to give it the index of the face that I want to calculate planarity for. And I think that should probably be it. All right. So now let me create here a function that is going to be a public function. It's going to be accessible by everyone. It's going to return a number. It's going to be called planarity, and it takes a mesh, and it takes an integer called ID, which is going to be the ID of the face. I'm actually going to write here face ID. All right. And here we're going to perform the calculations of that planarity. All right. What is that calculation going to look like? Well, let's take a look. Diagram, of course, we're going to sketch as we typically do. It's very useful. So first of all, we're going to do this for meshes inside of Rhino, because Rhino accepts meshes that have quad faces, which is actually quite unique. Typically, many other environments will only allow you to work with meshes that have triangles as faces, and we know that triangles are always planar. So all this work that we're doing right now here would be kind of useless. So we're going to focus on those faces that are quads, that have 4 vertices as opposed to 3, where the triangle will always be planar. So if we think of those faces, we can see how 4 vertices always will form a quad face that may not necessarily be planar, because one of the vertices may be off their plane. So what does that mean? It means that for any 4 vertices, I can always choose 3 of the vertices, form a plane between those 3 vertices, and then calculate how far away the 4th vertex is from that plane that I've calculated. Now, how do I do that manually? Well, I could use Rhino, take planes, calculate offsets from planes, blah, blah, blah. But you know me already, and this is advanced development in Grasshopper, so we're going to use a little bit of vector algebra to make this process more optimal, faster, and also more elegant. So what is that going to be? The way that's going to be is that in order to calculate this offset, first of all, I'm going to create 2 vectors between 3 points in my face. Those 3 points can actually be whichever 3 points, all right? And then what I'm going to do is that I'm going to calculate the cross product of those 2 vectors. The cross product, if you remember, is a vector that is perpendicular to the 2 vectors that generated the cross product. So what that means is that vector is going to be perpendicular to the plane that is formed by the 3 points or the 2 vectors that we created from those 3 points. And now what we can do is take that point and project the point on top of the cross product vector. How do we do that? We can do that very easily by creating another vector that goes from the first point of the 3 to this point, and then projecting that vector on top of the cross product vector. That projection can be done using the dot product of 2 vectors. And I forget if I think I have cards that speak about all of this. So maybe the card will be showing up on the corner, or there will be videos. I have other videos talking about, there will be video links in the description if you want to know more about these geometrical relationships between vectors. Okay? So we're going to do that very easily. So how are we going to do that? Well, first of all, we're going to say, I'm going to get the face. I'm going to get the face. I'm going to get the face. So mesh face is going to be equal to m dot faces with an ID of the face ID. All right. So mesh face is a structure that gives us information about the face in Rhino. And then what I can do right away is I can say if face dot is triangle, then return 0. Return 0 because it's going to be a flat surface. There's no offset there's no vertex that has an offset between the other 3. Otherwise, if it's not, then we can do some calculations. So we're going to call the vertices, let's assume that they're going to be in clockwise order. So this is going to be A, B, C, and D. All right, and let's assume that they have this nice orientation. So what we're going to do is, first of all, I'm going to create a vector 3D, which is going to be AB, and it's going to be equal to face.b minus face.a. All right, a vector that goes between those 2 points. I'm going to be a little lazy here, so I'm going to create a vector AD, which is going to be equal to face D minus face A. All right, and I'm using the implicit operator just to speed things up a little bit. And last but not least, because I will need it, now that I'm at it, I'm also going to create the vector AC because I'm going to need it farther down the road. So here, var vector AC is going to be equal to face C minus face A. All right, those are the vertices of the, actually, no, wait. I am not, so face.A, this is an integer. Oh, this is pointing to, okay, so I need to redo this, sorry. So that would be mesh dot faces, and the face that is at the ID face dot A, all right, and then that's B, and then m dot face. Oh, what have I done? Mesh, and then face dot A. All right, and then I'm going to do the same here and here, here and here, and I'm going to close, 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 and close. All right, beautiful. I have the 3 vectors now. So now what I can do is I can calculate the cross product between AB and AD to calculate the perpendicular. So the cross product is going to be, again, I'm going to be lazy here. Instead of typing everything, I'm just going to say the cross product is going to be vector 3D dot the cross product between AB and AD. All right, beautiful. And then what I'm going to do is I'm going to unitize this vector. I'm going to do that because in order to calculate the proper length of AC projected on top of the perpendicular vector needs to be unitized. It's part of how this works. So I'm going to unitize it, and then after that, what I'm going to do is I'm going to calculate the projection of AC on top of the cross product by using the dot product. So that could be vector 3D dot product, but as you can see, we don't really have the dot product as a static method in the vector 3D class. That is because Rhino, out of the box, uses the simple multiplication sign as the dot product operator. So what we can do is we can say AC, which is the vector, I'm going to multiply it by the cross product, and this operation is the dot product. All right. And then, beautifully, what we can do now is that now that we have that dot product, what we can do is we can return the absolute value of this vector. All right, which is not a vector, it's actually a double. Let me actually do that just in case, so there is no, and let me make sure that the cross product is a vector and this is a double, so that there's no confusion. I'm going to be using the absolute value because it might be the case that point C may actually be right here, and that the projection may actually be negative. But since for us, in planarity terms, whether if the offset is in one direction or the other, it doesn't really matter. And if we actually did the cross product between the 2 other vectors in a different order, the vector will be pointing in the other direction. It doesn't really have a meaning for us. We just want the absolute value of that distance. So that's why we are going to return the absolute value here. Okay? And then, so that is a vector, that is a function that calculates planarity or the offset for a mesh and a particular phase ID. And for offsets in the Y position, I want to store this value. Let me output that so that we can take a closer look and see if things are going well. So that's going to be offsets. I'm going to run this. I'm going to, I already have an error, so that sounds great. And let me plug in here some panel to take a look at the error. Mesh phase operator, blah, blah, blah. Cannot be applied to operands of that Rhino mesh phase and Rhino mesh phase. Okay, so what have I done wrong? So yes, okay, so yes, you're right. So this, when we access the A, B, C, or D property of a phase, what that is giving us is the ID of the vertex that is in that phase. So using that ID of the vertex to get a phase is actually not cool. So what we actually want to do is we want to get the vertex, and then also you cannot subtract a phase from another phase. That doesn't make sense as an operation, but you can subtract 2 vertices and then get a vector between them. All right. Okay, and we still have a problem. What is going on? Mesh does not contain a definition for vertex. Sorry, vertices. Wow, it's been a long stream today. Sorry, vertices. There you go. And okay, so now it's working. So now we can see that we have all those values of the offsets. And let me take a look at the bounds of this. So, oopsies. So I'm going to copy this. I'm going to bring it here. And then we can see that Basically, no face is really planar. That's interesting. At least all of them has a tiny, they have a tiny bit of an offset. What if I crank this down? Will all these ones become planar? Now we have something that is almost very, very close to planar, but no quad. It's exactly purely planar, which is also quite interesting. But anyway, so I'm going to keep this value high so that I get a lot of non-planarity from these faces here. And okay, so we have all those values. What is the next thing that we're going to do? What we're going to do is that we're going to normalize those values as we did before. So what are we going to do? We're going to, for this one, we're going to get we're going to find the maximum value. We don't care about the minimum because in this case, when we normalize, we want to keep 0 at 0. So we want to keep faces that don't have any offset. We want to keep them as like that, even if in our collection we don't have any. So I'm going to say double dot minimum value, and then here if of is greater than maximum value, then make maximum value this value of the offset, so that we calculate the maximum. And now we're going to calculate the normalized values, and that's going to be equal to a new double array with the same amount of elements. And then we're going to do a for loop where we're going to iterate over all the faces. So I is less than norms dot length and I plus plus, and then for each value we're going to normalize it. So we're going to say we have to do this in a second for loop because we need to know which one is the maximum value before we do the normalization. And we don't know that until we have finished going over all the faces. So that's why it's two separate for loops as opposed to doing the whole thing in just one. So now what we're going to do here is we're going to say normalize values in the I position is going to be equal to, in the offsets, whatever value, and we're going to divide this by the maximum. In this case, we don't divide by the range, we don't divide by anything, but because we know that we have no negative values and because we want to keep 0 wherever it is. All right? And then let's output now here norms, and then let's take a look at that. So if that makes sense. So tiny values, and then let's take a look at the range of values for the normalized values. Now it's from something a little smaller to 1. Okay, so that looks great. And with this, I think we are probably quite ready to, to now display those colors on as part of the preview. So I'm going to turn the preview on, all right? And then I'm going to explain how we're going to do this, which is going to take a little bit of extra effort as opposed to the previous example. Okay, let me draw a diagram here. And let me draw a diagram here. I'm going to save this. And okay, new. That is not going to fly. So then instead what we need to do is we just need to say, well, let me take this full, let me make a mesh, and then we color the 4 edges so that we have a homogeneous. And then if we do that for the other 4 meshes, we may have okay. All right. Let's do this. For this example, we're not going to be able to use the technique that we used before of the false colors in the mesh exactly as we used it before for the following reason. Think about this, because what we're trying to represent is the planarity of the whole face. The technique that we were using before was associating color values to individual vertices. What that means is that if I choose a color for this vertex, for this vertex, for this vertex, this one, this one, this one, this one, this one, this one, what would end up happening is that, let's say, for example, that we choose a very high color for the corners, a very strong red, and a very strong white for the center of the mesh. What we would get when that mesh gets color and render is something like this. We get Rhino, and the graphics environment does some color interpolation between the vertices of the mesh so that throughout the face, within the face, the color changes in a gradient way, in a linear way, and makes some areas of the face, makes them darker or makes them lighter based on the vertex colors. And that is not exactly what we want here. What we want here is for each face, what we will want is to have a solid color that represents the planarity of that face, and the next face we want to have some other solid color. We don't want any of these interpolation transitions, etc., etc. So in order to render that pre-visualization, we're not going to be able to work by applying vertex colors to the whole mesh as we did before, but we're going to have to use the following technique, which is going to be for each face of the mesh, we're going to go face by face. And what we're going to do is we're going to create a new mesh that is just the 4 vertices of the face that we're looking at, and that is only going to have that one face. So for that one mesh, what we're going to do is to the 4 vertices, we're going to add the exact same vertex color, whatever we calculated in this case. We're going to add the exact same color so that the color of that face, which is not a face anymore, is a full mesh that only has this one face, so that the color is homogeneous. There's no interpolations. And then we're going to repeat this process for every single face. We're going to create new meshes for each one of the faces that it's only the face itself. We're going to apply the vertex color to the 4 vertices, and we're going to achieve a solid color without interpolations between those vertices. So in a way, we're cheating a little bit, because instead of representing a mesh with vertex colors, we're basically representing as many meshes as faces our original mesh has. And then for each one of those tiny meshes, I'm coloring the 4 vertices with the same color so that we have a flat, uniform color representation for that mesh. That we can do pretty easily and pretty fast with the rendering engine. It takes a bit more of computing cycles, but it's not a very heavy operation, I think so. So let's see how to do that code-wise. All right. Okay. Okay, so And back here. We are back with our C# script definition. I'm going to run it. I'm going to do the thingy that we typically do, which is taking the mesh and saying render mesh, and then making sure that we have values that are that have been passed here. So, for example, I'm going to say render mesh is going to be equal to m. All right. But I'm also going to pass in all those values that I have calculated, especially the norms one, the one that had the normalized values. So, for example, normalize offsets, and I'm going to make sure that normalize offsets is equal to this array that we generated. And I do this, as I said in the previous video, to scope that information so that it's available to all the other overrides, the ones that are going to be doing the pre-rendering and the pre-visualization. So now we're going to go to the draw viewport meshes, which is, I'm going to remove the actual wire ones, and I'm going to here write the base code that we're going to need in order to render each one of the faces of the original mesh as a full mesh by itself. What is that going to look like? Well, it's going to look something like this. First of all, here I'm going to iterate over all the faces in the mesh. So I equals 0, I is less than render mesh dot faces dot count, and then I plus plus. All right, and then what I could do is I could calculate the color that I want to assign to this particular face that I'm going to be rendering. As we said before, I can take the normalized value, that's going to be normalized offsets by the value of I, and then what I can do is I can calculate the value of the color as an integer. I'm going to make sure that that's clear, and I can do integer of 2055 times that normalized value. Okay, so that could be something that I can do. I can, for example, yes, and I can calculate that, and that's going to be either red or green, or we can figure out how to do that. All right, and then what I would like to do now is, from my general mesh, the one that has all the faces, I need to extract one mesh that is basically the 4 vertices of the face that I'm looking at and the vertex colors applied to that mesh. So, because that sounds like an involved operation, I may want to create a function that does that. So let me prototype this. So what I want is a mesh. So I'm going to call that M. And let me imagine a function that creates a mesh from a face. And it takes, for example, it's going to take the full mesh that I need, is going to take the ID of the face that I want to extract, and it's going to take the color that I want to apply to the vertices. All right. If I have this mesh and this mesh becomes this sub mesh of the original one, then I will be able to use what I did before, which is args.display.draw mesh with false colors and the mesh that I have extracted from the original one. All right, which already contains the vertices. We're still designing this. We haven't implemented this. But then the condition is that we need a function that, given a mesh and given the ID of a face, extracts a new mesh with vertex colors in there. All right, that's going to be actually quite simple to do, a little tedious, but it's actually quite simple to do. So let me say, I'm going to create, no shouting here. I'm going to create that function that is going to return a mesh, and it's going to be called mesh from face. It's going to take as an input a mesh, it's going to take as an input the face ID, is going to take as an input the color as an integer, and then we will convert that here as well. And what are we going to do now? Okay, so let's start simple. First, I'm going to create an empty mesh, all right, with nothing inside of it. So new mesh. The next thing that I'm going to do is from the mesh that came in as an argument, I'm going to extract the face that I'm interested. So mesh face is going to be equal to mesh.faces and face ID. So now I have the face from the original mesh that I want to turn into a new mesh. So you know what? Let me do that here. So now, to the new mesh that I have created, the first thing that I need to do is I need to add the 4 vertices of this face. So how is that going to do? Mesh, vertices, add, and the vertex that I need to do, add is from the original one, the original mesh, vertices, that one that is at position face.a. All right? And I'm going to do this 3 times. All right? B and C. And because the mesh may have triangular faces, why not, right? Well, at this point, I'm going to check if we're good. So I'm going to say if face dot is triangle, if this face is a triangle, then I'm going to stop here and I'm going to say m dot faces, then add a face between the vertices in position, so the vertices in position 0, 1, and 2. So because I added them in order, they're going to maintain the same order. All right. Otherwise, if it wasn't a triangle, then I need to add my 4th vertex. So that's going to be D. And I'm going to add a face between vertices in position 0, 1, 2, and 3. The one that I just added here. All right. At this point, I have a mesh that has 1, 2, 3, or 4 vertices, and that it has a face between the vertices that I have generated. So this mesh is already valid. I could return it and I could render it, right? It's just a tiny mesh with 3 or 4 vertices and 1 face. The only thing is that before returning M, which is what I'm creating, what I want to do is I want to add vertex colors because I want that to be rendered on the screen nicely. So to the 3 or 4 vertices, I need to add the vertex color here. How am I going to do that? Well, I'm going to say, well, I could do the same thing. I could do if else, but I'm going to be a bit more programmatic here. For I is equals 0, I is less than m dot vertices dot count. So I'm going to iterate over however many vertices this new mesh has. And then what I'm going to do is I'm going to do m dot vertex colors dot add, and I'm going to add a new vertex color to that. So here we have the value from 0 to 255. So let me use that as the red, for example. So color, or yes, let me add that as red, for example. And wait, I think, is that it? Because we have the function and this is already pre-implemented. Can we do this? Is this working? I got an error. 128, error at 128. So that's norm offset. So I have a typo here. Norm offsets, and this is, wait, it's working. Choo-hoo, it's working. Look at this thing. How beautiful is this? So now we have in our mesh, which has been pre-visualized here, so I can turn it on and off. All right. And we have faces that are very bright, very bright red, if they're very non-planar, and faces that are very dark, if they are very planar. What's interesting is that turns out that these ones are fairly planar because of the geometry of how I've generated the surface. This, and because of the discretization, these faces also tend to be very planar, whereas the ones that are in the slope of the mountain, if you will, they have a pretty large offset. So if I were to change the discretization here, you can see, how nice is this, right? Oh, this is very nice. Actually, I forgot how cool was this. Yep, 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 yep. All right. Now you can get a bit more creative with colors and then do like a rainbow of colors, go from black to white, go from I don't know. But yeah, that's actually pretty nice. Look at this and look at these crosses, how they represent. So maybe yeah. So it looks like this worked out. All right. How awesome is this? Like, seriously, like, why do you not? How does someone not want to spend all their time and their life doing this kind of stuff? Huh? Beautiful. Okay, so let's wrap this up. It was kind of a long exercise, but I hope you've learned a bunch of stuff in on the way. We made a custom rendering for vectors, which is somewhere here. Oh yeah. Wait. Something I forgot here is that we need to add the bounding box here. Yes. So remember, render mesh dot get bounding box in false. All right. Just to wrap things up. So we have the vector. We have the vector, we have the curvature analysis, we have for the surface, we have the Gaussian curvature, and for the same surface, we have the planarity of the faces. Okay, so this has been pretty good for practicing pre-visualizations, but also like all this whole like mesh geometry rendering false colors was actually a pretty interesting exercise, I have to say. I hope you learned a lot with this. Anyway, this ended up being more of a computational geometry exercise than perhaps the previous ones, but I thought it was pretty cool anyway. Without further ado, we're going to move on to the next video in this series. We're going to learn more about advanced scripting and development in Grasshopper. But in the meantime, if you liked what you saw, you may want to consider liking this video or subscribing to the channel or dropping a message or sharing some of your fantastic work with us on the Discord server where we have conversations throughout the week offline. Okay? All right, beautiful. Thank you very much, and I'll see you on the next video. Bye-bye. All right. And then let's record the introduction. And we are good. Okay? Beautiful. Let me show stuff here. Let me hide this. Hello, and welcome to over and over again. Hi, this is Jose Luis here, and welcome to another video in this series, Advanced Development in Grasshopper. For this exercise hands-on video, what I would like to do is I would like to put to practice some of the things we've learned in the previous video where we saw how to generate custom previews and custom renderings on the screen for Grasshopper components. And I would like to put that to practice with a few exercises, such as, for example, extending the example that we did for visualizing vectors to display the length. Instead of in the tiny corner here, I would like to display it in 3D and keep the orientation to the camera that we're viewing, and also with controllable parameters such as the color of the arrow, or for example, the size of that text on the screen, or whether if it shows up or not in the first place. So that will be an extension of that. I would also like to show you how to create graph analysis graphs. That was very redundant. So how to display the idea, how to display those graphs, those nice graphs that Rhino generates for the curvature of a curve. This is actually going to be super straightforward and be able to then customize, the size and the samples, etc., etc. That's going to be super cool as well. And then this is probably the most important part of this exercise, the one that took the longest to record, is going to be also the idea that for any particular surface, what I can do is that I can also preview on that surface. Let me hide this. I can preview on that surface things such as, for example, the Gaussian curvature. The Gaussian curvature being a measure of how a surface is very concave or is very convex, all right, and which areas it is one or the other. This is a very interesting exercise to do because in order to represent this and render this, it relies on using this technique called a false color mesh, which is basically meshing the surface, the nerve surface, and to each one of the vertices apply a color that represents whatever we want to analyze. In this case, Gaussian curvature. It's a bit more tedious, but it uses this other function that we didn't see in the previous video, which is draw mesh previews. All right, that's going to be useful, for example, for curvature, or for example, if I want to do an exercise where what I take is any mesh with quad panels or with triangular panels, and what I render is a graph of the planarity, or how much of an offset each one of the faces of the mesh has. So you can see that in this one, for example, what we can render is for each one of the quads, each one of the square faces of this mesh, we can color it with a value of red that represents how non-planar it is. So we can see that for this surface, this area is very flat. You can see that these areas in the slope of the hills are very curvy. And we can see that actually, very interestingly, because of the nature of how we drew this, these stripes of faces here are also fairly planar compared to the other ones, which I think is extremely, extremely cool, if you ask me. So all with things you're going to learn in this exercise is doing custom previews, but at the same time, we're going to spend quite some time learning this technique, the false color vertex technique for meshes, which is extremely, extremely popular and very widely used to color meshes according to particular analysis, solar analysis, energy analysis, geometry analysis, like the ones we're going to be doing in this exercise, etc., etc. So I welcome you to join this. It's going to take some time, but I'm going to be using a lot of diagrams and explain things conceptually, so you may actually learn a lot of new stuff with the excuse of doing custom previews. All right. And without further ado, let's dive in and let's get our hands dirty into custom preview components scripted in C# within Rhino and the Grasshopper environment. Oh, that was a lot. It took us 3 hours to record this. I need to start getting better at doing this. Okay, so how did you feel about this video? Because it took forever. Do people sit through a 1.5 hour video of me just like going back and forth and blah, blah, blah? I'm not talking about the live stream. I'm talking about when the video is edited and ready for viewing. Do people watch these videos? I really have no idea. Okay, so I really don't have a clue. Anyway, that was it for today on my end. Was it? Yes. That's all I wanted to cover. I wish we had time for making more videos, but at least this one, I think, content-wise and exercise-wise, came out really nicely, actually. So you watch things at 2 times the speed. That also helps, obviously. Yeah, that's a good thing for YouTube as well. Okay, cool. I appreciate that. I'm going to call it a day today. It was quite a long live stream, so I will edit the video and publish it next week at some point. And in the meantime, it was a pleasure to hang out with all of you, as usual. Consider subscribing to the channel if you like the work we do. And join the Discord if you want to hang out and chat throughout the week and be nerdy. And yeah, and see you on next live streams. Bye bye. Thanks a lot. Bye bye.